Welcome back, everybody, to another video lecture from Mrs. Semino. Tonight we're going to be talking about the periodic table trends, and this matches up with your 6.3 video notes. The first trend that I want to talk about is the atomic radius. The definition for this is the distance from the center of the atom's nucleus to its outermost electron. Now when we look at these pictures here, we're going to see that we have two atoms. So really the way that we measure the atomic radius is we measure from the nuclei of one atom to the nuclei of another when they're bonded with each other. And then we have to go ahead and divide this in half. So I just want to remind you that this is the diameter. This would be just the radius. You guys see, like, this is supposed to be a circular atom. Here is the nucleus, and this length right here would be considered the radius. The reason that we have to measure it from nuclei to nuclei is that the edge of the electron cloud is a little bit fuzzy. It's not like a solid thing, and so you can't really measure to the edge of like where that last electron is. So this is the best way to do it, to measure from nuclei to nuclei. And then take that value and divide it by 2 to get the radius. Now, like I said, we were going to talk about the periodic table trends tonight. So you're going to need to know the definition of each trend, like what each trend is, and then how does it occur on the periodic table. So the periodic trend for atomic radius says that the atomic size increases going down a group. Okay, so if we look over here going down a group, you can see that the atoms are getting bigger. And this happens because of an increase in the principal quantum number. That's kind of a fancy way of saying energy levels. So remember, hydrogen has 1 energy level, lithium has 2, sodium has 3 energy levels. So of course those energy levels are getting further away from the nucleus, so your atom is increasing in size. Now the trend for atomic radius is a little bit different, or maybe it's different from what you would have thought it would be. As you move across the periodic table going in this direction, the atoms actually get smaller. So if you look at this picture over here, do you see how the atoms are getting smaller? And the reason for this is the increase in the number of protons in each atom. So beryllium only has 4, neon has 10. So that's probably something that you already knew. But neon is smaller because the increased number of protons means a stronger nuclear charge, okay? It's kind of like, think of like magnets, like, so it's like a stronger attraction to its outer valence electrons. So this neon is able to pull its valence electrons in closer than beryllium is. Another example to look at is aluminum has got 13 electrons, argon has 18. Since argon has 18 electrons, argon is able to pull those valence electrons in closer to the nucleus than aluminum is, and that's why argon is a smaller atom. So a general trend that you can remember for discussing atomic radius is that atoms get larger as you move from right to left and going down diagonally on the periodic table. So some kids like to remember the diagonal trends. It's also helpful to remember that atoms are going to get larger as you go down a group because they're getting more energy levels, and atoms are getting larger as you move in this direction because you have a fewer number of protons on this end of the periodic table than this. And again, more protons means an increased nuclear charge, meaning that you have the ability to pull those valence electrons in closer to the nucleus of the atom. Now on this slide, I want you to understand these two terms. I think we've talked about them before, but I just want to go over them again. We have a cation, that's a positively charged ion, like a cat is positive, and then anions are negatively charged ions, and I usually use the example of like and kind of go along together. Well, since cations are losing electrons, they're going to decrease in size. So you're going to have your atom here, it'll become a smaller ion. Anions, they're gaining electrons, so you're going to increase your repulsion forces. So that means that those electrons aren't going to want to be as close to each other as they once were, so your atoms actually get larger. Here's something that we've discussed before, but it's so important that I want to make sure that everybody understands it. So the question that we might ask is, why would an atom want to lose or gain electrons? It does this because atoms want to have a stable electron configuration. And for all elements, except for hydrogen and helium, this means having 8 valence electrons, and this is called the octet rule. Now, if you remember back to a video or two before, remember it was those noble gases that had full valence shells, and so they obeyed the octet rule. We also said that those noble gases were very stable, meaning that they're not reactive. So it goes back to our reason here that atoms want a stable electron configuration. So sometimes we'll say that they want to have a noble gas configuration. Elements in a group form ions of the same charge. These charges follow a specific pattern. The elements on the left side of the periodic table form positive ions. Remember, those were called cations. And elements on the right side of the periodic table form negative ions or anions. So please take a second and copy down the common ionic charges that we're going to see. We'll discuss these a little bit more in class, but remember over here we have lithium and we have sodium. They have one valence electron, so as we'd said in the past, is it going to be easier for those atoms to lose their one electron or to gain 7 more electrons to have those full shells? Well, it'll be easier for it to lose its one electron, and therefore it'll gain this 1 plus charge. On the other hand, if we look over here at the halogens, halogens have 7 valence electrons. So would it be easier for a halogen to lose its 7 electrons it already has or gain 1? Well, gaining 1 will be easier, so that's why it develops that negative charge, because electrons have that negative charge. The next trend to discuss is ionization energy. The definition for ionization energy is it is the energy needed to remove an electron. So atoms with a high ionization energies hold on to their electrons very tightly. Atoms with low ionization energies are more likely to lose one or more of their electrons and gain a positive charge. And just so we know, the units we use when we measure ionization energy are kilojoules per mole. Now here are the trends for ionization energy. Notice that it increases as we move up. And the reason for this is that those valence electrons are where those electrons would be lost from, because those valence electrons are the outermost electrons. Now, hopefully a simple explanation for this is that as you move up the periodic table, you're getting fewer and fewer energy levels. So for example, this might be hydrogen up here, and this might be potassium a little bit further down. If we notice the distance here, the distance between the nucleus and the valence electrons is very small, meaning that there's a strong attraction or a strong pull on those valence electrons. The distance here between the nucleus and the valence electrons, it's larger. So the attraction or the strength of holding on to those valence electrons is weaker here because they're further away. We sometimes tend to use this example is if you had a candy bar sitting right in front of you, you're going to be able to keep a good eye on it and nobody's going to be able to take that candy bar. But if you put that candy bar about 5 tables away, it's more likely to disappear because you can't keep such a good eye on it. It's not a perfect analogy to it, but sometimes it helps kids remember. And then ionization energy increases as you move across the periodic table. Again, this is because we have more protons, so we have an increased nuclear charge, meaning that we're able to hold on to those valence electrons even tighter on elements on this end of the periodic table. So the overall trend we have is this diagonal increasing from left to right across the table. Now, something that we might see this year are called successive ionization energies. Most often, we're going to be talking about the first ionization energy. This is the energy required to remove the first electron. But then there's also second, third, fourth, and it keeps going. So again, the second ionization energy is the energy required to remove the second electron. And then the third removes the third electron. What you'll notice is that there is a trend. So let's say your first ionization energy was 200. You might have a trend of 400 here, and then this one might be 1200 kilojoules per mole. And so the idea behind this is that the first electron is pretty easy to remove, the second electron is more difficult to remove, and the third is even more difficult. So going back to our candy bar example, the first time you lose an electron or your candy bar, it happens. But you're not going to let it happen again, and you're certainly not going to let that candy bar disappear for that third time. Okay, we're almost done. 2 more trends to talk about. This one is called electron affinity, and it is the energy change that occurs when an atom gains an extra electron. It is the measure of an atom's attraction or affinity for an extra electron. Remember what we said about the alkali metals? They were wanting to lose their electrons, so the energy change is not going to be very big. Over here, though, notice that we have a dramatic, it's much more stable when atoms gain electrons over here in the halogen section. So this is what I was trying to explain on that last slide. The electron affinity values for many elements are negative because they release energy when they gain an electron. Atoms that have a greater attraction for an added electron, like those halogens, have a more negative electron affinity value. And the trends for electron affinity is that elements on the right side of the periodic table have more negative electron affinities than elements on the left side, the metals. And the exceptions here are noble gases actually have positive electron affinities, meaning that there's no way in heck that they want to be getting another electron. And then finally, probably the most important trend that we'll see on the periodic table and we'll use when we get to bonding is electronegativity. The definition for electronegativity is an atom's ability to attract electrons in a chemical bond. Periodic trends for this are, as you move up the group, you're going to go ahead and increase in your electronegativity. Again, this has to do with the distance from the nucleus to the valence shells. So we have less distance up here, so there's that increased attraction. And it increases as we go from left to right across the table. Again, more protons on this end of the periodic table, increased nuclear charge, so it's going to want to grab and steal. It has a stronger ability to grab and steal other atoms' electrons. And of course, you need to know that fluorine is the most electronegative element with an electronegativity of 4.0. These values are measured kind of in decimal numbers. We'll see the trends on the back of your periodic table. So in tonight's lecture, you guys, please make sure you're paying attention to atomic radius, how ions change in size, electron affinity, ionization energy, and electronegativity. Please look back at your notes and make sure you know those trends. Thank you. See you in class.